Okay, so a typical function that we might get for the flow model, which is what I mean by the water flowing out of the tube or the bottle, okay? Thing we did last week. That might be a typical function, okay? That function would actually probably fit our data, not real well, but well enough that we would accept this as at least a function that could fit the data if we had a little different size tube, okay? Okay, so to graph this function, we don't graph this by plotting a lot of points. We graph this by putting it into this form. Okay? It goes into this form by one of two methods. One involves a quadratic formula, one involves completing the square. Okay? And the first thing we'll probably do is use a quadratic formula, since it tells you so much. Or complete the square, which is something you should know how to do, but people almost never do. Okay? And we'll learn to do this. But the quadratic formula is actually fairly easy because everybody's taken my advice from last week and they now know how to write out the quadratic formula, right? I hope so. But if you forgot that I told you you really need to be able to do that, please don't come in here Thursday not knowing how to do that. You won't understand what you need to understand if you don't know the quadratic formula. Okay? Okay, so, well, I'm saying that we can see how to do this without having to make a big old table and plug in a lot of points, and we don't even know what points are going to give us what we need to know. Okay? If we see this as a transformation of our basic squaring function. Like, we start with a basic squaring function, and we vertically stretch it by a factor of negative 0.01, meaning we compress it down to 1/100th of its height and flip it over. Now, if you remember what we did, I think a week ago, you know exactly what I mean by that. We haven't compressed anything that much, but we have to do that to get our flow model, okay? And then we shift everything up k units, okay? But then there's another shift we have to do. We have to shift the vertex. Now we know that the graph, because you made graphs, your graphs almost all look something like this, don't they? Okay? Well, that's part of a parabola. Or it should be if we got accurate data. Or it's very close to being part of a parabola. And the parabola is going to bottom out. And then even though the water doesn't rise back up in the container after it flows out, the rest of the parabola would continue, so you have something that looks like a parabola. So you're looking basically at the left-hand side of a parabola that has exactly the same shape as the y equals x squared graph, because every parabola has the same shape. I mean, depending on how you scale your graph, it might look wider, it might look narrower, right? So if you're allowed to widen and narrow it and move it this way and move it this way, whatever this parabola is can come from your basic y equals x squared parabola, okay? And then the question is, your vertical stretch is going to be just this number here, this whatever's in front of t squared, okay? Then you got to translate the vertex, which was originally at the origin, over to wherever the vertex of the actual parabola is. Okay? Well, you could take your graph and estimate where the vertex is. Okay? And maybe that vertex is over here. You got to move over 100 units here, and then you got to maybe move up 20 units here, or whatever. Okay? So one thing I'm going to ask you to do is take the graph you already made from your data and see where you think this parabola would level off before it starts going back up. Okay? So you estimate what this would be and what this would be. Okay? Now for the number out in front here, it's not going to be negative 0.01, but it'll be something kind of like that. Many of you already have numbers. Okay? If those numbers are right, then you know how to get them, but it's just, that comes out of the simultaneous equations, right? Solve the simultaneous equation, that's the A. Okay? Whatever you get for A, that's a number that goes there. Going to tell you how much to squash that thing down. It's going to be a negative number, so you will have to invert it. And actually, I just lied. It's not inverted. It's straight up and down, isn't it? So actually, your A should be positive. And yeah, I just did another stupid thing, but that's okay. Get used to it. Okay. The B should be negative. When you do your quadratic model, you probably don't have them in front of you. You probably don't remember what your A, B, and C were. But your B number was probably negative. If you did it right, it should be negative. Okay? Your A number should be positive. Your B number should be negative. Your A number should be a small number, like 0.01, something in that general range, 0.02, 0.005. And your B is going to be negative. Okay, now, that's the context. So, this, whatever number it is you move over here, this is your H, and this is your K. The number out in front here is your horizontal stretch number, which actually, being small, really compresses things, okay? So there's the H and there's the K. Does that make, you don't understand why, or if you do, that's great, you probably take the exam right now. But that will be your H, that will be your K. Okay? Wherever the vertex of this thing is, you can tell what H and K are. And you can use the quadratic formula in a fairly straightforward way to find the vertex. We're probably not going to have time to tell you that, how to do it, but it's straightforward enough. Okay? If you complete the square, you can figure out what H and K are. You can figure out what these numbers would really be. Okay? So, I'm going to talk again about vertical shifts, vertical stretches, and horizontal shifts. We've talked about vertical shifts and vertical stretches. Those are easy to understand. Horizontal shifts aren't that hard if you remember the rule, but the rule goes in the direction opposite the direction you think it's going to go.